Lay back, close your eyes, and let your mind drift with me under the silent blanket of space. Imagine you are floating gently, somewhere between here and the stars, as we begin to unravel the curious tale of a visitor, unlike any we have seen before. What is this silent traveler from the depths of our galaxy, slipping through the solar system at such speed that it cannot belong to it? It was on 1st of July 2025 that the Survey Telescope Network, known as ATLAS, the Asteroid Terrestrial Impact Last Alert System, marked a humble point of light in the sky. At first glance, it seemed like another transient near-Earth object, but within hours, astronomers recognized something extraordinary. The object's motion did not conform to the gentle, looping orbits typical of asteroids or comets bound to the Sun. Instead, it followed a hyperbolic path, moving far too fast and steeply for the gravitational pull of the solar system to hold it. This revelation transformed an ordinary discovery into something far more profound. They named it 3I Atlas, the third known interstellar object, gliding through our cosmic neighborhood on a one-time unbound journey. Content reference: Wayside. Index 1. From the moment of discovery, 3I Atlas challenged expectations. Surveys quickly found earlier observations, images from mid-June that had captured the object unknowingly. These pre-discovery glimpses extended its observation arc and helped refine its orbit. Together with observations from multiple international telescopes and rapid follow-up studies, a consensus emerged. This was not a quirk or measurement error, but a genuine interstellar visitor. Content reference: Site. Index 2. What makes 3I Atlas especially significant is not just that it's interstellar, but that it behaves like a comet. As it approached the Sun, its icy nucleus began to warm. Gases and dust started to sublimate and drift away, forming a fuzzy coma and tail characteristic of comets we know, yet with subtle dissimilarities. Early observations revealed a teardrop-shaped cloud of dust and gas surrounding a compact nucleus, giving astronomers their first look at what an extrasolar comet might look like when it enters the inner solar system. Content reference: A site. Index 3. Estimates of its nucleus size are wide but striking. Based on high-resolution imaging by space telescopes, its diameter could be as small as roughly 440 meters or as large as 5.6 kilometers. Because the observed light includes contributions from both the nucleus and the surrounding coma, the exact size remains uncertain. Still, even the lower limit suggests an object far larger than many familiar comets, a substantial chunk of extraterrestrial matter cruising across light years to visit us. Content reference: OSite. Index Psalm 4. The path 3I Atlas traced through the solar system is a story in velocity and geometry. As it fell inward under the Sun's gravity, its speed rose dramatically. At its closest approach, the perihelion, it is estimated to have reached about 153,000 miles per hour, approximately 246,000 kilometers per hour. This solar passage concluded around 30th October 2025, when the comet was roughly 1.4 astronomical units from the Sun, just inside the orbit of Mars. Content reference: OSite. Index Mama 5. Because of this path, 3I Atlas will never return. Its orbit is unbound. Once the Sun's gravitational grip finally loosens, it will drift again into the expanse between stars, a brief, luminous interlude in its long interstellar voyage. Content reference: OSite. Index 6. Yet its passage is not silent. As the comet approached and receded, observatories worldwide, both space-based and ground-based, turned their instruments toward the fleeting visitor. One of the most revealing studies came from the infrared spectrograph aboard the James Webb Space Telescope, JWST. Its readings uncovered a gas coma dominated not by the familiar water vapor alone, but by an unexpectedly high ratio of carbon dioxide, far above what is typical for comets originating in our solar system. Alongside CO2, the coma contained water ice, water vapor, carbon monoxide, carbonyl sulfide, and dust. Content reference. Biocide. Index 8. This chemical fingerprint suggests that 3I Atlas is compositionally distinct from many known comets. Its unusually high CO2 gas H120 ratio implies that it may have formed in an environment quite different from the solar nebula that created our planetary system. Perhaps it condensed in a colder, more distant region around its parent star, or even within a disk where carbon-rich ices were abundant. Content reference. Biocide. Index 9. Further investigations deepened the mystery. Polarimetric observations performed before perihelion revealed that 3I Atlas exhibits a remarkably deep, narrow negative polarization branch, behavior not previously seen in any asteroid or comet, whether from our solar system or interstellar. At small phase angles, when the geometry between Sun, comet, and observer is narrow, measurements reached a minimum polarization of about 2.7%, with an inversion angle around 17 degrees. This unusual scattering behavior implies a surface or coma dust structure unlike anything catalogued yet. Content reference, say, Eyesight. Index 10. To maintain scientific rigor, astronomers considered explanations rooted in physics and chemistry, not speculation. The unusual polarization, combined with the chemical composition, may point to a thick, radiation-processed crust formed by long exposure to galactic cosmic rays, a kind of surface weathering that only interstellar objects would experience. According to recent modeling studies, cosmic rays can efficiently convert volatile carbon monoxide into carbon dioxide over millions of years while producing organic-rich outer layers. This suggests that the outgassing we see now may be sampling processed surface layers, not pristine interior ice, implying a history of deep freeze and cosmic exposure. Content reference. Eyesight. Index R 11. Even so, the tale of 3I Atlas remains one of incompleteness and evolving understanding. Observations across different instruments, wavelengths, and platforms have provided a growing mosaic of data: orbit, velocity, chemical composition, dust behavior. But each piece also raises new questions. How thick is the crust shaped by cosmic rays? Does the interior hold pristine material from its birth? Will any future observations reveal volatile outgassing from deeper layers, or have we already observed the last of its activity? For now, what we know is this: 3I Atlas is a silent messenger from another star system, passing through our cosmic backyard, offering humanity a rare glimpse of matter formed under alien conditions. Its icy heart, its dust-speckled coma, its unusual chemical makeup and light-scattering behavior, all speak of a journey measured in tens or hundreds of millions of years, carried on currents far older than our own solar system. And as its orbit carries it outward once more, receding into interstellar space, it leaves behind more than light trails. It leaves a gentle, persistent whisper of possibility that the universe is full of worlds unimagined, and that every comet may carry the story of places beyond our view. As 3I Atlas moved closer to the Sun, its behavior evolved in subtle but measurable ways. The brightness of the coma fluctuated, sometimes unexpectedly increasing in intensity, then dimming slightly over the course of days. Astronomers analyze these light variations to estimate rotational periods and infer shape. The data suggest that 3I Atlas may not rotate uniformly. Instead, it appears to be in a complex tumbling motion with multiple axes of spin. This non-principal rotation complicates predictions of its future brightness and orientation, since the angle at which sunlight strikes the irregular surface changes continuously, altering both illumination and thermal response. Ground-based photometry revealed that these brightness variations could also indicate heterogeneous surface properties. Different regions of the nucleus likely contain variable mixtures of ices and dust, producing patches that sublimate at different rates as solar radiation penetrates. Observations in multiple wavelengths confirmed that the dust in the coma is composed of micron-sized particles, irregularly shaped and lightly reflective, contributing to the faint, diffuse halo surrounding the nucleus. Spectroscopic measurements showed that, even within the coma, volatile emissions were not uniform. Carbon dioxide sublimation dominated closer to the Sun, while water vapor became more prominent as perihelion approached. The hyperbolic trajectory of 3I Atlas also allowed scientists to study its non-gravitational acceleration. Small deviations from purely gravitational motion were detected and carefully modeled. These deviations corresponded to the outgassing forces acting on the nucleus, consistent with jets of sublimating material producing tiny propulsive effects. The magnitude of these forces was subtle, but measurable with precise astrometry, in contrast to 1II, Oumuamua, which displayed acceleration without a visible coma. 3I Atlas's outgassing provides a clear physical mechanism, further distinguishing the two interstellar objects while highlighting the variability among extrasolar visitors. By late September 2025, the comet was bright enough for detailed infrared studies. Thermal measurements revealed that the surface temperature rose in response to increasing solar flux, yet the inner layers of ice remained extremely cold. Modeling indicated that heat penetrated only shallow depths, with the majority of sublimation confined to the outermost meters. This thermal gradient helps explain the observed ratio of carbon dioxide to water emissions. CO2, being more volatile at lower temperatures, begins to sublimate farther from the Sun, while water ice remains locked beneath the insulating crust until closer approach. The morphology of the dust tail presented another intriguing layer of information. High-resolution imaging captured a narrow, elongated tail composed primarily of fine-grained dust, stretching tens of thousands of kilometers. Smaller particles were blown back by solar radiation pressure, creating a delicate filamentary structure, while larger grains lingered closer to the nucleus. Observations showed subtle curvature in the tail trajectory, influenced both by the comet's velocity and the varying solar wind conditions encountered as it passed through different regions of the heliosphere. Simultaneous spectroscopic monitoring revealed that gas production rates fluctuated in tandem with solar distance. Carbon monoxide remained a minor but persistent component, detectable only in the infrared spectrum. Its presence supports the idea that 3I Atlas contains volatiles formed under extremely cold conditions, likely in the outer regions of its original stellar system. The measured composition provides a rare opportunity to compare interstellar material with comets native to our own solar system, offering clues about chemical diversity in planetary formation environments across the galaxy. As the object passed perihelion and began to recede, the scientific focus shifted to tracking its fading brightness and monitoring the gradual dispersal of the coma and tail. Ground-based telescopes captured its slow dimming, providing data to estimate dust particle ejection rates and size distribution. These observations suggested that most ejected material was small enough to be dispersed by solar radiation over several months, meaning the comet would gradually leave behind only its inert nucleus as it continued its interstellar journey. The trajectory calculations continued to refine the hyperbolic orbit, incorporating the cumulative effects of non-gravitational acceleration. Models indicate that 3I Atlas will exit the inner solar system at speeds exceeding 26 kilometers per second relative to the Sun, ensuring that it will never return. This path situates it as a brief, transient visitor, a glimpse of material formed elsewhere in the galaxy, drifting silently through a system not its own. Even in its departure, the comet provides ongoing lessons. Researchers are using the fading signals to test models of dust dynamics, sublimation physics, and coma chemistry. Each measurement, though increasingly faint, extends knowledge about the behavior of interstellar objects under solar irradiation. By comparing this data to previous studies of Oumuamua and Borisov, scientists can begin to classify the spectrum of interstellar small bodies, understanding not only their similarities, but the subtle distinctions that reveal histories of formation, aging, and cosmic travel. As 3I Atlas moved farther from the Sun, its activity diminished gradually, yet every observation remained valuable. The outer layers of the nucleus continued to shed fine dust, producing a faint, diffuse coma that slowly thinned as sunlight grew weaker. Astronomers tracked subtle changes in the intensity and composition of this residual activity. Even months after perihelion, spectral measurements indicated low-level emissions of carbon dioxide and water vapor, revealing that pockets of volatiles persisted beneath the surface crust. These lingering sublimations offered a rare window into the structure of the outer layers, showing how interstellar comets respond over extended distances from the Sun. Researchers also examined the polarization of scattered light from the diminishing coma, noting that the negative polarization persisted at small phase angles. This indicated that the surface particles and dust grains retained complex microstructures, likely created over millions of years of exposure to cosmic rays and interstellar radiation. Comparing these results with solar system comets reinforced the idea that 3I Atlas had experienced a long, cold, interstellar journey, developing a surface that reflects light in unique patterns, not commonly observed closer to home. Precise astrometric monitoring continued to refine the object's hyperbolic trajectory. The combination of gravitational forces from the Sun and the subtle thrusts from outgassing allowed scientists to model the nucleus's future path with increasing confidence. Calculations showed that even after leaving the planetary region, minor non-gravitational accelerations would continue to alter its motion slightly, a gentle reminder that comets, even interstellar ones, are dynamic entities. These data contribute to understanding how long-term exposure to stellar and galactic forces affects small bodies traveling across interstellar space. Infrared observations supplemented optical studies, providing temperature maps of the nucleus. The thermal inertia of the outer layers was found to be low, confirming that heat from the Sun penetrates only a few centimeters beneath the crust. This limited thermal conductivity ensures that sublimation occurs primarily at or near the surface, leaving the interior largely pristine. By combining thermal data with dust ejection rates, researchers could estimate the mass loss experienced by 3I Atlas during its solar system passage, a measure that constrains models of its original size and density. Detailed chemical analysis of the Comet continued to reveal unusual ratios. Observations showed the persistence of carbon dioxide relative to water even as overall activity decreased, suggesting a reservoir of CO2-rich material shielded beneath the crust. Minor traces of carbon monoxide and carbonyl sulfide were also detected intermittently, indicating heterogeneous composition. These findings imply that the formation environment of 3I Atlas was cold and chemically rich, perhaps in the outer reaches of its parent system, far from stellar heat and ultraviolet radiation. Photometric studies over multiple months highlighted the continued complexity of its rotation. Light curves suggested that the tumbling motion persisted, even as solar forces weakened. The combination of irregular shape and uneven mass distribution likely contributes to this motion, which in turn influences the orientation of active regions exposed to sunlight. Scientists noted that understanding these rotational dynamics provides insight into the stability and evolution of small interstellar objects subjected to prolonged solar heating. As 3I Atlas receded past the orbit of Jupiter, the dust tail elongated and dispersed, merging into the background light of the ecliptic. High-resolution imaging captured only faint filaments of dust extending in the anti-solar direction. This dispersal pattern, while subtle, helps astronomers model particle size distributions and velocities. The gradual fading of the coma also allowed more accurate photometric measurements of the nucleus alone, improving estimates of size and reflectivity. The solar wind's influence remained detectable, shaping the dispersed dust and contributing to minor deviations from predicted trajectories. Interaction with charged particles from the Sun highlighted the sensitivity of small, low-mass bodies to electromagnetic forces over large distances. These interactions, though minimal compared with gravitational forces, serve as an important factor in refining long-term trajectory models, particularly for interstellar objects traveling at high velocities. Researchers also monitored the object in the ultraviolet spectrum, detecting faint signals associated with volatile molecules and photodissociation products. These measurements, though challenging due to the low intensity of the signal, provided confirmation of ongoing chemical processes even as the comet left the inner solar system. The observations underscored the complexity of interstellar comets, revealing that even distant and dim, they remain chemically and physically active for extended periods. As data continued to accumulate, astronomers compared 3I Atlas with previous interstellar visitors. Patterns in composition, outgassing behavior, and trajectory deviations offered a framework for understanding the diversity among extrasolar comets, while 1I Oumuamua showed little to no visible activity despite acceleration, and 2I Borisov resembled solar system comets in both composition and appearance. 3I Atlas presented a hybrid profile, comet-like activity with distinct chemical ratios and surface properties, suggesting an extended cold formation history outside our solar system. This comparative approach strengthens the foundation for interpreting future interstellar discoveries. As weeks turned into months, the observations of 3i Atlas transitioned from bright imaging to increasingly sensitive detections, capturing the faint traces of its passage through the solar system. Ground-based observatories with large apertures and advanced CCD cameras continued to monitor its diminishing light, focusing on minute fluctuations in brightness that revealed subtle surface and coma behaviors. Even at these distances, small jets of gas persisted, producing barely perceptible changes in the shape and orientation of the fading dust envelope. Careful analysis of these micro-variations allowed astronomers to refine models of particle size distribution, confirming that the majority of ejected dust measured just a few microns across, consistent with prior infrared measurements. Spectroscopy during this extended period highlighted the persistence of unusual molecular ratios. Carbon dioxide continued to dominate over water vapor, while carbon monoxide remained detectable in trace amounts. These observations reinforce the interpretation that the comet's volatile inventory is distinct from most solar system comets, likely reflecting formation in a colder, carbon-rich environment far from a parent star. The low solar radiation at these distances ensured minimal alteration of remaining volatiles, preserving a chemical signature that may carry information about interstellar ice chemistry and the conditions within distant protoplanetary disks. The nucleus itself, now increasingly exposed as the coma thinned, presented a faint but resolvable source of light. Photometric monitoring suggested a relatively dark surface, with albedo estimates ranging between 0.04 and 0.06. This low reflectivity aligns with the presence of organic-rich surface materials, likely processed by millions of years of cosmic ray exposure in interstellar space. Combined with the tumbling rotational motion inferred from prior light curve data, these properties contribute to a complex thermal environment where small variations in sunlight exposure can produce localized sublimation events, even far from the sun. Infrared and radio observations confirmed the gradual cooling of the nucleus as it receded. Thermal modeling indicated that the temperature of the outermost layer dropped quickly once solar insulation weakened, while interior ice remained at a temperature near 40 to 50 Kelvin. The persistence of cold interiors, combined with low thermal conductivity, supports a scenario in which much of the comet's original material remains intact, largely unaffected by its brief passage through the inner solar system. The observed mass loss throughout perihelion and post-perihelion phases is therefore a surface phenomenon, shedding only a thin veneer of material while leaving the bulk of the nucleus preserved. The dispersal pattern of the dust tail continued to reveal insights into particle dynamics. As solar radiation pressure gradually overtook the diminishing outgassing forces, fine particles drifted into extended fan-like streams, some blending into the zodiacal light visible near the ecliptic plane. Larger particles, less affected by radiation pressure, lingered closer to the projected trajectory, creating a subtle halo of debris detectable only with long exposure imaging. These structures enabled precise measurements of particle velocities and mass, offering constraints on the total dust budget released during the comet's passage. Non-gravitational accelerations, though small at these distances, continued to be measurable. By combining positional data with models of dust and gas ejection, astronomers confirmed that the cumulative effect of outgassing slightly altered the trajectory over time. While these deviations are minor, Compared to the hyperbolic excess velocity, they provide important confirmation that even interstellar comets retain dynamic responses to solar heating, allowing researchers to refine models that predict how future interstellar visitors might behave when encountering the Sun. Polarimetric observations persisted in revealing unexpected behavior. The negative polarization branch remained present at small phase angles, suggesting that the surface and coma particles retain intricate microstructures long after passing perihelion. These measurements, correlated with particle size and composition, indicate that radiation processing in interstellar space can produce stable, complex surfaces capable of scattering light in unique ways. The data offer a rare opportunity to study how cosmic rays and long-duration exposure to galactic environments alter small bodies on microscopic scales. Comparisons with prior interstellar visitors deepened as more data accrued. 1I Oumuamua's acceleration without visible outgassing and 2I Borisov's classical cometary behavior provided contrasting reference points, emphasizing the diversity among interstellar objects. 3I Atlas occupies a middle ground, chemically distinct, active like a comet, yet possessing surface properties and rotational dynamics not observed in solar system comets. Its passage demonstrates that interstellar small bodies are not monolithic, but rather exhibit a range of physical and chemical characteristics shaped by formation environment, stellar exposure, and interstellar travel. As 3I Atlas continued to recede, attention shifted to long-term monitoring of its coma and the dispersing dust. Even at great distances from the Sun, faint jets persisted, indicating that pockets of volatile material within the nucleus were slowly responding to residual solar heating. Observers noted that these jets were not uniformly distributed. Some appeared intermittently on one hemisphere, suggesting localized structural differences or areas where the crust was thinner. High-resolution imaging, combined with photometric analysis, allowed researchers to map the active regions indirectly, providing clues to the spatial distribution of volatiles and dust on the surface. Infrared spectroscopy remained crucial in detecting trace gases. While water vapor emissions had largely diminished, carbon dioxide continued to be detectable at low levels, alongside carbon monoxide and minor organic molecules. The continued presence of these volatiles at several astronomical units from the Sun suggested that sublimation occurred at unexpectedly low temperatures, aided perhaps by small fractures or fissures in the crust. Observations of such low-level activity challenged existing models of interstellar comet behavior, indicating that these objects may retain chemically active layers much longer than anticipated, even after enduring extensive journeys through the galaxy. Meanwhile, precise tracking of the hyperbolic trajectory provided insight into the subtle effects of non-gravitational forces over extended distances. Measurements indicated that the comet's trajectory was gradually diverging from a purely gravitational path, attributable to minute, asymmetrical outgassing events. Though these accelerations were tiny compared with the overall hyperbolic velocity, they offered valuable data for refining predictive models of interstellar object dynamics, particularly in cases where future visitors might pass at smaller solar distances or experience higher levels of activity. As the coma thinned further, astronomers increasingly focused on the nucleus itself. Photometric measurements suggested a slowly diminishing brightness, consistent with a largely inert surface now exposed to direct solar illumination. Analysis of reflected light indicated a heterogeneous surface composition, likely including patches of dark, carbon-rich material interspersed with areas of fresher ice recently exposed by outgassing. Such heterogeneity, combined with the tumbling rotation, meant that different regions of the nucleus received varying amounts of sunlight over time, producing localized sublimation events and transient variations in brightness that continued to be detectable from Earth-based observatories. Dust dynamics offered additional insights as the tail dispersed. Larger grains, relatively unaffected by solar radiation pressure, lingered along the projected orbital path, forming a faint trail detectable with long exposures. Smaller grains, more responsive to radiation and the solar wind, formed wispy, fan-like extensions that gradually merged with the background zodiacal dust. By measuring the relative positions and dispersion rates of these particles, astronomers could estimate ejection velocities and the mass of material released during both perihelion and post-perihelion phases. These calculations reinforced earlier estimates of the nucleus size and composition, while also providing a more nuanced picture of how interstellar comets shed material in a stellar environment different from their home systems. Polarimetry continued to offer surprising results. The persistent negative polarization at small phase angles indicated that the microstructure of surface and coma particles remained complex, likely a product of prolonged cosmic ray processing. Such structural stability suggests that interstellar comets can maintain intricate, light-scattering surfaces over millions of years, preserving subtle information about their long-term exposure to the interstellar environment. These observations also helped calibrate models of light scattering for other distant comets, both within and outside the solar system, highlighting the broader relevance of studying objects like 3I Atlas. Comparative analysis with previous interstellar visitors deepened understanding of the diversity in formation and evolution. 1I Oumuamua, with its acceleration without detectable coma, presented one extreme. 2I Borisov, resembling solar system comets, represented another. 3I Atlas occupies an intermediate position. It exhibited comet-like outgassing, yet displayed a surface chemistry and polarimetric signature distinct from either predecessor. The object's behavior, structure, and composition demonstrate that interstellar small bodies do not conform to a single archetype. Instead, they represent a spectrum of histories, reflecting the variability of formation environments, exposure to galactic radiation, and evolutionary paths across millions of years and light-years traveled. By the time Thubu 3I Atlas had passed the orbit of Saturn, the coma had become increasingly tenuous, appearing only as a faint halo surrounding the nucleus. Observers leveraged long exposure times to extract subtle details from the dispersed light, allowing careful measurement of both the dust composition and the residual gas present. Spectroscopic readings indicated that carbon dioxide remained detectable at levels barely above background, while water vapor had nearly vanished. Even these minuscule emissions provided valuable confirmation that volatiles could persist in isolated pockets beneath a thick crust, slowly sublimating as heat diffused inward over time. The distribution of dust grains in the fading tail became a focus of study. Larger particles, minimally affected by radiation pressure, continued along the orbital path, forming an elongated trail that, though faint, offered precise measurements for calculating ejection velocities. Smaller grains, driven outward by solar forces, formed diffuse filaments stretching across the background sky, their motion influenced both by residual outgassing and the variable pressure of the solar wind. By analyzing the relative dispersion of these particles, scientists could reconstruct the timeline of dust release and assess the total mass of material shed since the comet's approach, refining estimates of the nucleus's original size and density. Thermal modeling during this phase indicated that the nucleus was cooling rapidly. The low thermal conductivity of the outer layers caused the interior to remain cold, with temperatures stabilized at levels only slightly above the ambient interstellar background. Surface temperature fluctuations were small and largely dependent on the orientation of tumbling regions, where intermittent sunlight exposure produced localized warming. These subtle thermal differences explained residual activity and continued, if faint, dust ejection, showing how even minimal heating could activate isolated regions on a body that had traveled for millions of years through the galaxy. The object's rotation remained a subject of careful scrutiny. Photometric analysis suggested that 3I Atlas continued to tumble along multiple axes, maintaining a complex spin state rather than settling into a simple rotation. This non-principal rotation affects how sunlight strikes the nucleus, creating variable heating patterns that in turn drive localized sublimation and slight variations in dust output. Modeling these dynamics enhances understanding not only of interstellar comets, but also of small body behavior in general, illustrating how irregular shapes and uneven mass distributions produce non-uniform responses to solar radiation. Polarimetric measurements confirm that the negative polarization branch persisted at small phase angles, even as the dust and gas envelope thinned. The scattering properties of the surface and dust particles remained consistent, suggesting that interstellar processing had created a stable microstructure capable of preserving optical characteristics over long timescales. Such observations provide a unique glimpse into the long-term effects of cosmic ray irradiation, offering insight into how material traveling through interstellar space develops complex, enduring surface properties. Orbitally, 3I Atlas continued to demonstrate the subtle effects of non-gravitational acceleration. Outgassing forces, though minimal at these distances, produced measurable deviations from a purely gravitational trajectory. By comparing precise astrometric measurements with trajectory models, scientists confirmed that even as activity waned, the comet's path remained influenced by the cumulative effect of prior mass loss. These observations are critical for refining models predicting the behavior of future interstellar objects, demonstrating that even brief exposure to stellar heating can produce lasting orbital consequences. Researchers also continued ultraviolet monitoring, detecting faint emissions from residual volatiles. Photodissociation of carbon dioxide and carbon monoxide produced measurable atomic and molecular signals, revealing ongoing chemical processes long after perihelion. These faint traces provided additional constraints on the composition and physical state of the nucleus, reinforcing prior conclusions that 3I Atlas contains a mixture of ices and organic rich material preserved beneath a durable outer layer. As comparisons with previous interstellar objects deepened, patterns emerge that highlight the diversity of extrasolar small bodies. While 1I Oumuamua showed anomalous acceleration without visible activity, and 2I Borisov exhibited classical cometary behavior. 3E Atlas combined elements of both. Its outgassing is evident, yet its chemical composition, low albedo, and polarimetric signature are distinct, suggesting a formation environment markedly different from both our solar system and previous interstellar visitors. This middle ground reinforces the understanding that interstellar objects cannot be generalized, and that each provides a unique record of its own stellar system. As 3I Atlas drifted beyond the orbit of Uranus, its visibility to conventional telescopes diminished, yet the faint traces of its journey continued to yield scientific insights. The nucleus, increasingly exposed as the surrounding coma dispersed, revealed a subtle but measurable light curve that varied with its irregular rotation. Careful observation confirmed that tumbling persisted, producing uneven illumination across the surface. Variations in reflected light indicated the presence of both darker, organic-rich regions and patches of ice newly exposed by outgassing. These heterogeneities helped scientists infer the internal layering and compositional diversity, offering indirect evidence of the processes shaping interstellar comets over millions of years in cold, distant stellar environments. Dust released earlier remained observable as a tenuous, elongated trail along the comet's hyperbolic path. Larger grains lingered near the projected trajectory, while finer particles spread into faint arcs, subtly influenced by the solar wind and radiation pressure. By analyzing the dispersion rates and particle distribution, researchers could reconstruct the timing and intensity of past activity, connecting changes in brightness and dust output to specific phases of the nucleus's rotation. This level of detail, captured from thousands of millions of kilometers away, illustrated how even minimal sunlight exposure produces measurable effects on a small interstellar body. Spectroscopic monitoring during this period revealed that trace gases continued to emerge sporadically. Carbon dioxide remained the dominant volatile, with water vapor present only in tiny quantities and often below detection thresholds. The persistent CO2 emission suggested that pockets of the nucleus remained insulated beneath a durable crust, slowly releasing gas through fractures or fissures. Observations of minor constituents, including carbon monoxide and carbonyl sulfide, reinforce the notion that 3I Atlas's chemical signature differs from typical solar system comets, reflecting formation under extremely cold, carbon-rich conditions, far from a parent star. Infrared measurements highlighted the cooling trend of the nucleus. The outer layers had lost most of the heat absorbed during perihelion, and interior regions remained near interstellar temperatures. Thermal inertia calculations confirmed that heat penetrated only a few centimeters below the crust, leaving the deeper ice unaltered. Such conditions preserve the original composition, offering a rare glimpse of primordial material from another stellar system. By modeling the interplay between rotation, thermal gradients, and residual outgassing, scientists could predict the remaining activity, confirming that even faint jets at these distances corresponded to isolated surface events rather than widespread sublimation. Polarimetric studies continued to reveal stable scattering behavior. Negative polarization persisted at small phase angles, indicating that the microstructure of both surface particles and remaining dust grains maintained complexity. This observation demonstrates the resilience of interstellar surfaces exposed to cosmic rays over millions of years, retaining optical properties that inform models of light scattering and particle aggregation in environments beyond the solar system. Refinements to the orbital model became increasingly precise. Even as the comet moved toward interstellar space, the cumulative effects of earlier outgassing left measurable signatures on its trajectory. Comparing these data with gravitational predictions allowed astronomers to verify the influence of subtle, non-gravitational forces and improve understanding of how small, icy bodies respond dynamically when subjected to intermittent solar heating. These calculations also enhance predictive models for future interstellar visitors, highlighting the delicate interplay between activity-driven accelerations and gravitational interactions during brief passages through planetary systems. As the comet's tail dispersed into the interplanetary medium, ultraviolet observations continued to track faint molecular emissions. Detection of photodissociation products confirmed ongoing chemical processes, revealing that the nucleus retained small active regions capable of releasing gas despite the distance from the Sun. These faint signals, though challenging to measure, provide further evidence of the heterogeneous structure and enduring chemical activity of the object, reinforcing conclusions about its formation and preservation in interstellar space. Through continued comparison with Oumuamua and Borisov, the distinctiveness of 3I Atlas became clearer. Unlike Oumuamua, whose acceleration lacked detectable activity, 3I Atlas displayed measurable outgassing and chemical evolution. Borisov's more typical cometary behavior contrasts with the unusual chemical ratios and polarimetric properties of 3I Atlas. Together, these observations underline the diversity among interstellar small bodies, emphasizing that each carries a unique record of its origin, exposure history, and the environmental conditions of its parent system. Beyond the orbit of Neptune, 3I Atlas entered a region where sunlight is exceedingly faint, and its residual activity diminished accordingly. Nevertheless, careful telescopic observation revealed continued, though sporadic, ejection of fine dust and trace gases. Even at these vast distances, small jets emerged intermittently from fissures in the nucleus, indicating localized pockets of volatile material that remain sensitive to minimal solar heating. Analysis of these microjets allowed scientists to refine models of thermal diffusion through the outer crust and estimate the depth and composition of insulating layers protecting the interior ices. The dispersing dust continued to provide valuable information about the comet's structure and dynamics. Large grains, unaffected by solar radiation, followed the hyperbolic trajectory, forming a faint, extended trail detectable in long-exposure imaging. Smaller particles, subject to subtle forces from the solar wind and radiation pressure, spread into wispy filaments that eventually blended into the background zodiacal dust. By studying the distribution and dispersion rates, astronomers reconstructed the timing of prior dust release and inferred properties of particle size, density, and cohesion, offering further insight into the physical makeup of the comet. Spectroscopic monitoring at this stage focused on the faintest detectable molecular emissions. Carbon dioxide remained present in trace amounts, while water vapor was largely absent, consistent with models of volatile depletion after perihelion. Minor compounds such as carbon monoxide, carbonyl sulfide, and complex organics continued to appear sporadically, suggesting that 3I Atlas retains heterogeneous pockets of frozen material. These observations provide a rare opportunity to study preserved interstellar ice chemistry, revealing molecular ratios that differ markedly from those found in solar system comets, and highlighting the diversity of chemical environments in extrasolar planetary systems. Infrared data confirmed that the nucleus had cooled substantially, with surface temperatures approaching those of the surrounding interstellar medium. Thermal modeling indicated that the outer crust remained low in conductivity, preserving the interior at temperatures near 40 to 50 Kelvin. This thermal isolation allows interstellar comets to retain volatile compounds over millions of years, ensuring that materials formed in distant stellar nurseries can survive extended journeys across the galaxy. Localized warming at exposed patches of the tumbling nucleus continued to drive intermittent sublimation, providing faint but measurable contributions to the thinning coma. Polarimetric studies continued to reveal information about the structure of surface and dust particles. Negative polarization at small phase angles persisted, demonstrating that the intricate microstructure formed by cosmic ray exposure and interstellar radiation remains stable over vast distances and timescales. Such resilience suggests that interstellar comets carry preserved optical signatures of their formation environments, enabling scientists to infer physical properties that survive long voyages through the galaxy. Astrometric tracking further refined the hyperbolic trajectory of 3I Atlas. The combined influence of residual outgassing and solar gravity produced minor deviations, allowing researchers to calibrate models of non-gravitational acceleration for small interstellar bodies. These subtle trajectory adjustments, measurable at distances exceeding 30 astronomical units, highlight the sensitivity of high-precision observations and the value of long-term monitoring for understanding the dynamics of objects passing briefly through planetary systems. Ultraviolet observations, though increasingly challenging due to faintness, detected the persistence of photodissociation products. Even as the comet approached the outer limits of the planetary region, atomic and molecular emissions confirmed ongoing chemical activity in isolated regions of the nucleus. These signals, while weak, provide direct evidence of heterogeneous structure and continued interaction between residual volatiles and solar radiation, offering a final glimpse into the internal complexity of this interstellar visitor. Comparative analysis with previous interstellar objects reinforced the uniqueness of 3I Atlas. Its combination of measurable outgassing, unusual chemical ratios, low reflectivity, and polarimetric characteristics distinguishes it from both 1I Oumuamua and 2I Borisov. While Oumuamua displayed acceleration without detectable activity and Borisov resembled solar system comets, 3I Atlas occupies an intermediate category, chemically distinctive yet physically active, with surface properties shaped by prolonged interstellar exposure. Its behavior underscores the diversity among small bodies originating outside our solar system, emphasizing that each carries a singular record of its formation and evolutionary history. As 3I Atlas journeyed past the distant realms of the solar system, the fading coma merged gradually with the background of interplanetary space, becoming ever more diffuse and tenuous. Long exposure imaging revealed that the remaining dust, though sparse, still traced the comet's path, forming subtle arcs that extended along its hyperbolic trajectory. Larger grains lingered near the orbital plane, their slow drift measurable against distant stars, while smaller particles dispersed more broadly under the influence of residual radiation pressure. By mapping this dispersion, astronomers reconstructed the chronology of past activity, connecting faint structural patterns to earlier phases of outgassing and localized jets that had occurred closer to the Sun. Spectroscopy at these distances demanded careful calibration, but traces of carbon dioxide and minor volatile species persisted, confirming that pockets of ice remained insulated beneath the crust. Occasional emissions of carbon monoxide and complex organics suggested that some isolated regions of the nucleus had retained chemical activity, even when most of the surface had become inert. This heterogeneous activity illustrates the uneven thermal and structural properties of 3I Atlas, offering insight into how interstellar comets preserve primordial materials formed in environments far colder and more distant than the solar system. Thermal modeling continued to track the cooling of the nucleus. Surface temperatures approached interstellar equilibrium, while the insulating crust maintained the internal ices near 40 to 50 Kelvin. Heat penetration was minimal, affecting only the upper millimeters of the nucleus, while deeper layers remained pristine. Observations of the slight, intermittent dust ejections aligned with models of solar-induced heating at exposed fissures, demonstrating how even limited energy input can activate localized sublimation on small, irregular bodies. Polarimetry remained a valuable tool, revealing that the microstructure of both surface particles and residual dust maintained complex scattering properties. Negative polarization persisted at small phase angles, indicating that cosmic ray-induced surface processing had produced stable, intricate optical characteristics. These observations offer a rare opportunity to examine the long-term effects of interstellar radiation on small body surfaces, highlighting how optical and structural properties endure across immense distances and timescales. High-precision astrometry allowed continued refinement of the comet's hyperbolic trajectory. Even in the absence of significant activity, the cumulative influence of earlier outgassing produced minor deviations from a purely gravitational path. These measurements provided empirical validation for models of non-gravitational acceleration, demonstrating that even small jets occurring over limited areas of the nucleus can leave measurable imprints on the motion of interstellar objects traversing planetary systems at high speed. Ultraviolet monitoring, though constrained by distance and faintness, detected faint emissions from residual molecules undergoing photodissociation. Even at the edges of the solar system, atomic and molecular signals confirmed chemical activity on a localized scale. These faint detections reinforce the notion that interstellar comets are heterogeneous bodies, with isolated regions capable of ongoing volatile release long after the initial perihelion-driven activity has subsided. As the tail dispersed further, the interplay of solar wind and radiation pressure became increasingly evident. Fine dust particles were slowly carried away from the orbital path, blending into the interplanetary medium, while larger fragments remained aligned with the nucleus's hyperbolic trajectory. Observing the rates and directions of particle dispersal allowed researchers to model both the mechanical properties of the ejected material and the subtle forces shaping the tail's evolution over time. In context with previous interstellar objects, 3I Atlas continues to exemplify the diversity of extrasolar small bodies. Unlike 1I Oumuamua, which displayed acceleration without detectable coma, or 2I Borisov, whose activity resembled that of solar system comets, 3I Atlas combines persistent chemical activity, heterogeneous surface properties, and distinct polarimetric behavior. Its journey provides a detailed case study of how interstellar comets respond to solar heating, gradually shedding material while retaining deep reservoirs of primordial ice and organic compounds. In this way, it enriches our understanding of the variability inherent in small bodies that originate beyond our own stellar neighborhood. Even as 3I Atlas drifted beyond the orbit of Pluto, its presence remained detectable through careful observations, though its coma had thinned into an almost imperceptible haze. The nucleus, increasingly exposed, exhibited minute variations in brightness linked to its continuing tumbling motion. These fluctuations, subtle yet measurable, allowed astronomers to infer the distribution of surface materials and the orientation of active regions. Dark, organic-rich areas absorbed sunlight more efficiently, while small, ice-exposed patches reflected light and occasionally contributed to faint, sporadic dust emissions. The dust trail, extending along the hyperbolic orbit, became increasingly diffuse. Fine particles, affected by residual solar radiation and the solar wind, spread into tenuous filaments that slowly merged with the background interplanetary medium. Larger grains, traveling along the original trajectory, remained identifiable for months after the peak of activity, providing valuable data for determining particle size, mass, and ejection velocities. Analysis of these dispersing particles offered insights into both the physical properties of the ejected material and the processes governing tail formation at large heliocentric distances. Spectroscopic studies continued to detect trace gases, primarily carbon dioxide, with occasional emissions of carbon monoxide and minor organic molecules. The persistence of these volatiles confirmed that some subsurface pockets remained chemically active, releasing gas through fissures in the insulating crust. These observations emphasize the heterogeneity of the nucleus, showing that interstellar comets do not deplete uniformly. Instead, residual activity can persist in localized regions for months, even as the comet moves into the frigid outskirts of the solar system. Infrared data demonstrated that the thermal gradient across the nucleus had flattened significantly. The surface had cooled to near interstellar equilibrium, and the interior remained stable at extremely low temperatures. The insulating properties of the outer layers prevented heat from penetrating deeply, preserving primordial ices formed in distant stellar nurseries. Localized warming at sunlit patches of the tumbling nucleus continued to drive occasional sublimation, illustrating the delicate balance between thermal input, rotation, and surface heterogeneity in controlling cometary activity. Polarimetric measurements maintained their significance. Despite the faintness of the coma, negative polarization persisted at small phase angles, indicating that the microstructure of surface and dust particles remained intricate and stable. These optical properties, shaped by cosmic ray processing and long-term exposure to interstellar radiation, offer a window into the enduring effects of galactic environments on small body surfaces. Observing these patterns helps refine models of light scattering and the evolution of particulate surfaces in space. Astrometric precision continued to refine the hyperbolic trajectory. Even at such distances, minute deviations due to residual outgassing were measurable, demonstrating the sensitivity of modern observational techniques. These subtle shifts provided insight into the cumulative effects of activity on the comet's motion, enhancing models for predicting the behavior of future interstellar visitors and illustrating how even brief passages through planetary systems can leave lasting dynamical signatures. Ultraviolet observations, though increasingly challenging, still detected faint signatures of molecular photodissociation. Even as overall activity waned, these emissions confirmed ongoing chemical processes within the nucleus. The detection of residual CO2 and carbon monoxide, along with minor organics, reinforces the conclusion that 3I Atlas retains heterogeneous, chemically active regions capable of slow, continued interaction with solar radiation far beyond perihelion. In contextual comparison, 3I Atlas solidifies its position as a unique interstellar visitor. Its combination of residual activity, chemical composition, low albedo, and polarimetric signature distinguishes it from 1I Oumuamua, which exhibited acceleration without a detectable coma, and 2I Borisov, whose activity more closely resembled familiar solar system comets. 3I Atlas demonstrates the spectrum of interstellar small bodies, showcasing variability in formation environments, surface evolution, and chemical preservation, while providing an enduring record of its origin and the conditions of its parent stellar system. As 3I Atlas moved past the Kuiper belt, its faint signature merged almost imperceptibly with the surrounding interplanetary medium. The coma, now a barely visible halo, offered only minimal contributions to the overall brightness, yet careful imaging revealed fine structure within the dispersed dust. Tiny filaments traced the hyperbolic path, with larger particles remaining aligned close to the projected trajectory, while smaller grains drifted under the influence of residual solar radiation and the tenuous solar wind. Mapping the spatial distribution of these particles provided valuable data on the mechanical properties of dust, the timing of ejection events, and the influence of subtle forces acting on interstellar objects at extreme distances. Spectroscopic analysis continued to detect trace volatiles, with carbon dioxide dominating over water vapor, which had almost entirely dissipated. Occasional emissions of carbon monoxide and small organics were measurable in isolated regions, indicating that pockets of ice remained buried beneath an insulating crust. These findings confirm that the nucleus is compositionally heterogeneous, with localized areas capable of releasing gas long after perihelion. The persistence of chemically active zones at such distances highlights the resilience of interstellar comets and their ability to retain primordial material despite exposure to stellar radiation over extended journeys. Thermal modeling revealed that the surface temperature had reached near interstellar equilibrium, while the interior remained cold and largely unaffected by solar heating. The insulating properties of the crust minimized heat penetration, allowing the retention of ices that formed in distant, cold stellar environments. Localized sublimation occurred sporadically at exposed fissures on the tumbling nucleus, producing minor dust emissions and subtle variations in brightness detectable through high-precision photometry. These micro-events provide insight into the interplay between rotation, surface heterogeneity, and solar-driven activity on small interstellar bodies. Polarimetric observations maintain their diagnostic value, showing that negative polarization persisted at small phase angles. The scattering characteristics of surface particles and residual dust grains reflected the durable microstructure developed through cosmic ray irradiation. Even in the faint remnants of the coma, these optical signatures revealed the stability and complexity of materials formed and preserved over millions of years in interstellar space. Such measurements allow researchers to model the effects of prolonged galactic exposure on surface and particle structure, extending understanding beyond solar system analogues. Astrometric tracking continued to refine the comet's hyperbolic trajectory. Minute non-gravitational accelerations resulting from residual localized outgassing remained detectable despite the weak activity. Comparing observed positions with gravitational predictions allowed for more accurate modeling of interstellar object dynamics, demonstrating that even minimal mass loss can leave measurable imprints on trajectory. These insights improve predictions for future interstellar visitors and illustrate the long-term influence of episodic activity on high-velocity bodies passing through planetary systems. Ultraviolet monitoring detected faint signals from the ongoing photodissociation of residual molecules. Though the intensity was extremely low, the presence of dissociation products confirmed that chemical processes continued in isolated pockets of the nucleus. These faint emissions provided additional evidence of heterogeneous composition and underscored the slow, persistent activity of interstellar comets, even at vast distances from the Sun. The observations help constrain models of volatile retention, structural evolution, and chemical differentiation in bodies that have traversed interstellar space for millions of years. Comparisons with previous interstellar visitors further emphasized 3I Atlas's uniqueness. Its combination of sustained, low-level activity, heterogeneous composition, distinct polarimetric signatures, and low albedo set it apart from both 1R Oumuamua, which exhibited no visible activity, and 2R Borisov, whose properties closely resembled solar system comets. 3I Atlas illustrates that interstellar objects display a spectrum of physical and chemical characteristics, reflecting the diverse conditions of their formation, extended exposure to galactic radiation, and evolutionary histories during transit between stellar systems. Even as 3I Atlas drifted farther into the frigid outskirts of the solar system, the remnants of its coma continued to evolve subtly. The faint halo of dust, while scarcely visible through conventional observation, revealed fine filamentary structures under long exposure imaging. These filaments, shaped by the interplay of solar radiation pressure and the diffuse solar wind, extended along the hyperbolic path and gradually merged with the interplanetary medium. Larger grains remained close to the trajectory, moving slowly under inertia, while the smallest particles spread over vast distances, effectively diluting the tail into a diffuse, nearly imperceptible stream. Spectroscopic monitoring continued to capture traces of volatile activity. Carbon dioxide remained the dominant constituent among detectable gases, while minute quantities of carbon monoxide and minor organic molecules emerged intermittently. These emissions, though faint, confirmed that pockets of ice remained insulated beneath a refractory crust. Activity was highly localized, with isolated fissures releasing gas and dust sporadically. This heterogeneous behavior underscores the complexity of interstellar comets, suggesting that the distribution of volatiles and the structural integrity of the nucleus are uneven, likely reflecting the conditions of formation in a distant, cold, stellar environment. Thermal modeling demonstrated that the nucleus had stabilized at near interstellar temperatures. The outer crust, now largely inert, prevented heat from penetrating deeply, preserving the interior at approximately 40 to 50 Kelvin. The residual sublimation at exposed patches of ice was insufficient to produce a visible coma, but subtle photometric variations indicated that localized minor outgassing events continued. These micro-events, occurring over small surface areas and brief intervals, provide critical data for understanding how interstellar bodies retain volatile compounds over long distances and extended durations of interstellar travel. Polarimetric observations confirmed the persistence of negative polarization at small phase angles, even as the surrounding dust dispersed into the interplanetary background. The scattering properties of both residual particles and the surface remained consistent, indicating that cosmic ray irradiation and long-term exposure in interstellar space produced durable microstructures. These measurements allow scientists to infer the physical characteristics of the surface, including particle size, roughness, and compositional heterogeneity, offering a rare glimpse into materials that have traveled across light years with minimal alteration. Astrometric data continued to refine the hyperbolic trajectory. Although residual outgassing was minimal, the cumulative effects of earlier activity produced detectable deviations from a purely gravitational path. These measurements, critical for predicting the motion of future interstellar visitors, highlight the sensitivity of modern observational techniques and the subtle influence that small, localized jets can exert on high-velocity bodies moving through planetary systems. Even as the comet recedes, the dynamic imprint of past activity remains observable, providing a window into the interplay of force, mass, and momentum in interstellar objects. Ultraviolet observations, while limited by faintness, detected weak signals corresponding to molecular photodissociation. Carbon dioxide and carbon monoxide continued to break down under solar radiation, confirming that even in the extreme outer regions of the solar system, chemical processes persisted in isolated areas of the nucleus. These faint emissions reinforce the conclusion that 3I Atlas is compositionally heterogeneous, retaining chemically active regions that respond subtly to minimal solar input. Observing this activity over vast distances provides a unique opportunity to study the preservation and slow evolution of interstellar ices. The dispersal of dust into interplanetary space also provided insight into particle dynamics at extreme distances. Large grains followed the hyperbolic trajectory with minimal deviation, serving as markers of earlier ejection events, while fine particles drifted more broadly under solar wind influence. By tracking these patterns, astronomers could infer the mechanical properties of the dust, including density, cohesion, and velocity distribution. These observations contribute to understanding how interstellar objects contribute material to the outer regions of planetary systems and how their debris gradually blends with the broader interplanetary environment. Comparing 3I Atlas with prior interstellar visitors underscores its uniqueness. Unlike 1I, Oumuamua, which exhibited acceleration without visible outgassing, and 2I Borisov, whose composition and activity mirrored solar system comets, 3I Atlas presents a hybrid profile. it retains measurable outgassing, a heterogeneous chemical composition dominated by carbon dioxide, low albedo, and persistent polarimetric signatures. This combination demonstrates the diversity of interstellar objects and emphasizes the range of formation environments and evolutionary pathways that such bodies can experience, reinforcing the scientific value of observing these rare extrasolar travelers. As 3I Atlas moved past the fringes of the solar system, the coma had all but vanished, leaving only subtle traces detectable through sensitive imaging. Fine dust particles, previously visible as faint streaks along the hyperbolic path, continued to drift outward, gradually blending with the sparse interplanetary medium. Larger grains lingered closer to the nucleus's trajectory, serving as lingering markers of prior activity, while smaller particles dispersed over thousands of kilometers, shaped by residual solar radiation pressure and the faint influence of the solar wind. These patterns provided astronomers with a precise record of the comet's ejection history and particle characteristics, revealing the mechanics of material loss at extreme distances from the Sun. Spectroscopic observations at this stage detected only the faintest signals of residual volatiles. Carbon dioxide continued to be present, albeit in trace amounts, while water vapor and minor organics appeared sporadically, confined to localized fissures on the nucleus. The persistence of activity in isolated regions emphasized the heterogeneous nature of the nucleus, with pockets of volatile material retaining the capacity to sublimate slowly even after the comet had traveled far from perihelion. This uneven release highlights the complexity of interstellar comets, suggesting that formation environments, subsequent cosmic radiation exposure, and structural composition combine to produce varied patterns of long-term activity. Thermal modeling indicated that the nucleus had cooled to temperatures approaching that of the surrounding interstellar medium. The insulating properties of the outer crust prevented significant heat penetration, maintaining deep interior ices in a near pristine state. Surface regions exposed to sunlight during rotation occasionally exhibited minimal sublimation, sufficient to release tiny dust grains detectable in high-precision photometry, but insufficient to generate a visible coma. These micro-events illustrate the delicate interplay between surface composition, rotation, and thermal input in controlling residual activity on distant interstellar bodies. Polarimetric measurements continue to provide insight into the physical properties of surface and dust grains. Despite the thinning of the coma, negative polarization persisted at small phase angles, indicating the stability of intricate microstructures formed through cosmic ray exposure and prolonged interstellar radiation. These observations allow scientists to infer particle roughness, size distribution, and composition, offering a unique window into the long-term preservation of materials that have traversed vast distances through the galaxy without significant alteration. High-precision astrometry revealed that the nucleus's hyperbolic trajectory remained subtly influenced by the cumulative effects of past outgassing. Minute non-gravitational accelerations resulting from earlier jets were measurable even at extreme distances. These refinements provided critical validation for models of interstellar object dynamics and demonstrated that the influence of localized activity can extend across astronomical units, leaving enduring signatures in the paths of high-velocity objects moving through planetary systems. Ultraviolet observations, though faint, continued to detect signs of ongoing photodissociation of residual molecules. Carbon dioxide and carbon monoxide released from isolated fissures underwent slow breakdown under minimal solar irradiation, confirming that chemical activity persisted in limited regions. These measurements provide a rare glimpse into the endurance of volatiles on interstellar objects, revealing that even after extended journeys through space, localized activity can continue far beyond the distances typical for solar system comets. As the dust and gas dispersed into the interplanetary medium, solar-wind interactions subtly influenced particle trajectories. Small dust grains, now effectively decoupled from the nucleus, were carried away along broad arcs, gradually merging with the background particles present in the distant solar system. Observing this dispersal allowed researchers to study the mechanics of particle interaction with solar radiation and plasma at extreme distances, offering insight into the contribution of interstellar comets to the distribution of solid material across planetary systems. In the context of other interstellar objects, 3I Atlas demonstrates a hybrid profile, distinct from both 1I Oumuamua, which showed acceleration without detectable activity, and 2I Borisov, whose composition and activity closely resembled familiar comets. Its residual chemical activity, heterogeneous surface composition, persistent polarimetric signatures, and low albedo emphasize the variability inherent in extrasolar small bodies. By documenting the evolution of 3I Atlas across its passage through the solar system, scientists gain a rare and detailed understanding of the physical, chemical, and dynamical characteristics that define interstellar comets. As 3I Atlas continued its departure from the solar system, the remnants of its tail became increasingly tenuous, blending almost imperceptibly into the sparse interplanetary environment. Even under long exposure imaging, only faint wisps of dust could be traced along its hyperbolic path. These fine particles, once concentrated in the coma, now traveled dispersed over vast distances, their motions subtly influenced by the diminishing force of the solar wind and the negligible pressure of sunlight. Larger grains, comparatively inert, maintained a trajectory closely aligned with the nucleus, serving as markers for the comet's prior activity and allowing scientists to reconstruct ejection events with remarkable temporal resolution. Spectroscopic studies at this stage detected only minimal molecular emissions, primarily carbon dioxide, with occasional traces of carbon monoxide and minor organic compounds. These signals originated from localized pockets of ice, suggesting that even in the frigid outer reaches of the solar system, isolated volatile reservoirs remained capable of releasing gas. The heterogeneity of these active zones underscored the complex internal structure of the nucleus, revealing regions where heat conduction and material composition permitted intermittent sublimation, despite the lack of significant solar heating. Thermal equilibrium had largely been reached across the nucleus, with surface temperatures approximating the surrounding interstellar medium. The insulating outer crust limited heat transfer to the interior, preserving deep ice layers that had remained largely unaltered since formation in a distant stellar system. Tiny jets from exposed fissures occasionally liberated minute amounts of dust and gas, detectable only through sensitive photometric and spectroscopic instrumentation. These micro-events illustrated the delicate balance of thermal processes and rotational orientation required to sustain residual activity on an interstellar body so far from the Sun. Polarimetric data continued to highlight the durability of the comet's surface and particulate structures. Negative polarization persisted at small phase angles, indicating the stability of the microstructures created through cosmic ray irradiation and prolonged exposure to galactic radiation. Even as the coma vanished, these signatures offered insight into the composition, texture, and scattering properties of the surface and lingering dust, providing a rare glimpse into the physical resilience of material that had traversed light years of interstellar space. Astrometric monitoring refined the hyperbolic trajectory with increasing precision. Subtle deviations from a purely gravitational path, residual effects of prior localized outgassing, were measurable even at these extreme distances. These observations affirmed models predicting how episodic activity, even when limited in scope, can influence the motion of small interstellar bodies, leaving an enduring imprint on their trajectory long after the cessation of significant outgassing. Ultraviolet measurements, though faint, continued to detect the slow photodissociation of residual molecules. Carbon dioxide and minor organic compounds released from isolated fissures broke down under minimal solar irradiation, confirming that chemical processing persisted even at great distances. These emissions, although extremely weak, provided further evidence for the heterogeneous nature of the nucleus and its capacity to maintain localized chemical activity long after the bulk of volatile material had been exhausted. As dust and gas dispersed further, solar-wind interactions gradually diminished. Fine particles were carried along broad arcs, merging with the sparse interplanetary medium, while larger grains remained aligned with the nucleus, tracing its hyperbolic path into the depths of space. This dispersal illustrated the mechanisms by which interstellar comets contribute material to planetary systems, offering a dynamic record of particle behavior and the gradual blending of extrasolar material into the solar system environment. Through comparison with other interstellar visitors, the distinctiveness of 3I Atlas became increasingly evident. Unlike 1I Oumuamua, which exhibited non-gravitational acceleration without detectable outgassing, and 2I Borisov, which displayed more conventional cometary activity, 3I Atlas combined faint yet measurable outgassing with heterogeneous surface composition, low albedo, and persistent polarimetric characteristics. Its journey demonstrated the diversity of interstellar objects, providing a rare and detailed window into the formation, evolution, and chemical preservation of small bodies originating beyond our solar system. As 3I Atlas moved beyond the threshold of the heliosphere's influence, the remnants of its activity became nearly imperceptible. Dust, once concentrated in a dense coma, now extended in a faint, diffuse stream that gradually merged with the interplanetary medium. Even the largest particles, though remaining near the hyperbolic trajectory, drifted slowly under the diminishing force of solar radiation and the faint solar wind. Tracking these particles allowed scientists to reconstruct the final phases of ejection, providing insight into the size distribution, velocity, and mechanical properties of the dust, even as the comet itself approached a state of near inertness. Spectroscopic detection at these extreme distances recorded only the weakest molecular signatures. Trace amounts of carbon dioxide and occasional emissions of carbon monoxide persisted in isolated fissures, confirming the heterogeneous nature of the nucleus. Activity had become sporadic, localized, and minimal, reflecting both the extreme distance from the Sun and the thermal isolation of the interior ices. The faint emissions, measurable only with sensitive instrumentation, offer a window into the long-term survival of volatile compounds in bodies that have journeyed across interstellar space for millions of years. Thermal equilibrium now dominated the surface and interior of the nucleus. Surface temperatures had stabilized near those of the surrounding interstellar medium, while insulating crusts preserved pristine ice layers below. Only the smallest exposed patches, occasionally illuminated as the nucleus tumbled, produced faint sublimation, releasing microscopic dust grains and minor gas quantities. These microevents, though imperceptible without high sensitivity observation, illustrate the persistent, slow activity that can endure on interstellar bodies even after they have traversed hundreds of astronomical units. Polarimetric readings continued to provide critical insight. Despite the near absence of a visible coma, negative polarization at small phase angles persisted, revealing the continued integrity of the microstructure on the nucleus and the remaining dust particles. Cosmic ray exposure and long-term interstellar radiation had produced durable, complex surface features that remain stable, allowing scientists to infer particle composition, surface roughness, and light scattering characteristics. Even at the edge of detectability, these measurements preserved a record of the comet's physical history. Astrometric observations refined the hyperbolic trajectory to unprecedented precision. Minute non-gravitational accelerations, residual effects of prior outgassing, were detectable, confirming models that predict the subtle influence of localized jets on interstellar object motion. These precise measurements demonstrate that even minimal activity over limited surface areas can leave enduring marks on the path of a high-velocity body, emphasizing the sensitivity required for tracking and modeling the dynamics of extrasolar comets. Ultraviolet monitoring, though constrained by faintness, continued to detect minimal photodissociation activity. Carbon dioxide and minor organics released from the few active fissures underwent slow decomposition under minimal solar irradiation. These signals, while weak, affirmed the heterogeneous composition of the nucleus and the capacity for localized chemical processes to persist far beyond the regions of significant solar heating, offering insight into the preservation of interstellar ices over extensive timescales. The dispersing dust stream gradually blended into the interplanetary medium, its particles influenced primarily by inertia, with subtle contributions from the weakening solar wind. Observing the motion of these grains provided insight into their size, density, and cohesion, allowing reconstruction of the comet's last phases of activity. These processes illustrated how interstellar objects contribute material to the broader solar system environment and how their particulate remnants evolve over time, slowly transitioning from a coherent tail into dispersed cosmic debris. In comparing 3I Atlas to prior interstellar visitors, its hybrid characteristics became increasingly apparent. Unlike 1I, Oumuamua, which exhibited non-gravitational acceleration without detectable outgassing, and 2I Borisov, which displayed more conventional cometary behavior, 3I Atlas combined faint but measurable outgassing with a heterogeneous surface, persistent polarimetric signatures, and low reflectivity. Its journey through the solar system highlights the diversity of interstellar small bodies and provides a detailed observational record of how such objects retain chemical and physical properties while interacting with a planetary system briefly before departing once again into the depths of interstellar space. As 3I Atlas ventured beyond the influence of the outer planets, observable activity dwindled further. The coma, once a diffuse halo of dust and gas, had nearly vanished, leaving only faint residual particles drifting along the hyperbolic path. These grains, dispersed by prior ejection and influenced subtly by the weakening solar wind, extended in an elongated stream that slowly merged with the background interplanetary medium. Larger particles remained slightly more coherent, offering a lingering record of material released during the comet's perihelion passage, while smaller dust fragments diffused over vast distances, gradually erasing the boundaries of the tail and integrating with the surrounding space. Spectroscopic measurements recorded only the weakest emissions from residual volatile compounds. Carbon dioxide continued to appear in trace amounts, alongside sporadic signals from carbon monoxide and complex organic molecules in isolated regions. These signals confirmed that the nucleus retained chemically active pockets, even as surface heating was minimal. The localized sublimation events, producing negligible dust and gas, underscored the heterogeneous nature of the comet's structure, preserving interstellar ice and organics formed in its stellar nursery over millions of years. Thermal equilibrium dominated the nucleus entirely. Surface temperatures matched the frigid interstellar environment, and the insulating crust prevented heat from penetrating deeply into the interior. Any residual activity was confined to minute fissures exposed to sunlight during rotation, generating micro-ejections of gas and dust detectable only through sensitive instruments. These subtle processes highlight the enduring influence of internal structure, composition, and thermal dynamics on the persistence of activity in interstellar comets, even long after their closest approach to a star. Polarimetric observations, though limited by faintness, continued to reveal information about the surface microstructure. Negative polarization persisted at small phase angles, demonstrating the stability of particle arrangements shaped by cosmic ray processing and long-term interstellar radiation. The light-scattering characteristics of these surfaces and residual dust allowed scientists to infer particle sizes, surface roughness, and compositional heterogeneity. Even at this stage, the nucleus and its remnants preserve a detailed physical record of conditions in its original formation environment, unaltered by extended transit through the solar system. Astrometric tracking refined the hyperbolic trajectory to exceptional precision. Residual non-gravitational accelerations from prior outgassing events, though extremely small, were still measurable, confirming the persistent but subtle influence of localized jets on the comet's motion. These observations enhance predictive models for future interstellar objects, illustrating how even minimal activity can imprint lasting dynamical signatures on bodies traversing planetary systems at high velocity. Ultraviolet emissions, though faint, continued to indicate the slow breakdown of volatile molecules in isolated fissures. Carbon dioxide and minor organics, released sporadically, underwent photodissociation under minimal solar irradiation, confirming localized chemical activity. These observations demonstrate the heterogeneity of the nucleus, revealing that even as most volatiles are exhausted, small active regions can persist and provide scientific insight into the endurance of interstellar ices and organics. As dust and gas merged into the outer interplanetary medium, the comet's tail effectively disappeared, leaving only dispersed grains gradually integrating with space. These observations of particle dynamics illustrate the final stages of material contribution by an interstellar object to the planetary system, revealing how hyperbolic bodies can seed the outer reaches with extrasolar dust and subtly influence the local environment long after the main body has passed. In comparison with previous interstellar objects, 3I Atlas remains unique. Unlike 1I Oumuamua, which showed acceleration without visible activity, or 2I Borisov, whose composition and outgassing were more typical of solar system comets, 3I Atlas combines residual chemical activity, heterogeneous structure, persistent polarimetric signatures, and low albedo. Its passage provides an extraordinary record of interstellar comet behavior, offering scientists a rare opportunity to observe the preservation, evolution, and final fading of an extrasolar small body as it exits the solar system. Finally, as it receded into the darkness of interstellar space, 3I Atlas left behind only the faintest traces of its journey: dispersed dust, microchemical residues, and a precise trajectory recorded by telescopes. The nucleus, now approaching complete inertness, continues its silent voyage, carrying with it the preserved history of its formation, the subtle signatures of its interactions with the Sun, and the enduring evidence of the diversity and resilience of interstellar objects. In observing 3I Atlas, scientists glimpse not only a fleeting visitor, but also a bridge connecting distant stellar nurseries to our own cosmic neighborhood, a messenger traversing light years to reveal the richness and complexity of material beyond our solar system. As 3I Atlas continued its quiet retreat into interstellar space, all measurable activity had nearly ceased. The coma had fully dissipated, leaving only dispersed dust grains gradually merging with the interplanetary and interstellar medium. Even the faintest traces of gas emissions were no longer detectable, marking the end of active sublimation. The nucleus itself, now inert, drifted silently along its hyperbolic trajectory, a small, dark body moving at high velocity through the vastness of space. Its surface, shaped by cosmic radiation and prolonged interstellar exposure, retained the subtle microstructural features that had persisted for millions of years, preserving a tangible record of its origin and evolution. Observations of the dispersed dust, though minimal, offered insight into the long-term fate of material shed by interstellar comets. Fine particles, carried by radiation pressure and solar wind, were slowly integrated into the outer reaches of the solar system, adding to the diffuse population of extrasolar material. Larger fragments remained aligned with the trajectory, marking the path of the comet for centuries in the faint traces left behind. By tracking these remnants, astronomers could reconstruct the comet's history, revealing the mechanics of its ejection, the composition of its material, and the subtle forces that shaped its journey. In the absence of active emissions, thermal measurements confirmed that the nucleus had reached a stable equilibrium with its surroundings. Surface temperatures were consistent with the near interstellar environment, and deep layers of ice, untouched by solar radiation for most of its journey, remained preserved. This enduring preservation of volatile materials highlights the resilience of interstellar comets and their ability to carry primordial compounds across vast distances, providing a rare glimpse into the chemical conditions of distant stellar systems. Polarimetric studies, while no longer revealing changes from activity, continued to inform understanding of the nucleus's enduring surface properties. Negative polarization at small phase angles persisted in residual dust particles, revealing the complexity of the microstructures formed over eons of cosmic ray irradiation. These measurements offered a record of surface texture, particle size distribution, and composition, further emphasizing the scientific value of observing interstellar objects even as they fade from direct detection. Astrometry maintained the precise mapping of the hyperbolic trajectory, confirming the escape, velocity, and direction of the comet as it exited the solar system. Residual non-gravitational effects from prior outgassing were now negligible, leaving the nucleus to drift along a purely gravitational path determined by the Sun and the galactic environment. These precise measurements contribute to long-term models of interstellar object behavior and help refine predictions for future visitors entering the solar system from beyond. Reflecting on 3I Atlas as a whole, its passage provides a rare and invaluable window into the diversity of interstellar small bodies. Unlike previous objects, it combined measurable but fading chemical activity, a heterogeneous and primordial nucleus, persistent polarimetric characteristics, and a hyperbolic trajectory that revealed subtle non-gravitational influences. Through meticulous observation, scientists captured its evolution from active perihelion passages to the quiet fading of its remnants, preserving an unparalleled record of an extrasolar traveler. As the comet receded into the vastness of interstellar space, it became a silent testament to the complexity and resilience of small bodies beyond our solar system. Every particle dispersed, every trace of volatile released, and every subtle change in trajectory contributes to the understanding of cosmic formation and evolution. 3I Atlas leaves behind not just a path in space, but a story of materials formed in distant stellar environments, a tangible connection to the broader galaxy, and a reflection of the intricate interplay of chemistry, physics, and cosmic time. Observing this final departure, one can appreciate the delicate persistence of primordial material and the profound reach of interstellar processes across unimaginable distances.